In the vast darkness of space, there exist remarkable stellar metropolises that have witnessed the birth of our galaxy, the mysterious globular clusters. Globular clusters are massive spherical collections of hundreds of thousands of stars, bound together by gravity into perfect cosmic snow globes. In their dense cores, stars are packed incredibly close, often separated by distances smaller than that between Earth and our Sun. The Great Hercules Cluster, M13, is one of the most spectacular globular clusters visible from Earth, containing over 300,000 stars. These ancient stellar cities formed over 13 billion years ago, making them among the oldest known objects in our universe. Our Milky Way is surrounded by about 150 globular clusters, forming a vast halo that traces the outline of our galactic home. Globular clusters have a distinctive structure, densest at their cores and gradually thinning out towards their edges, shaped by eons of gravitational interactions. Most stars in globular clusters are ancient red and yellow stars, formed in a single burst of star formation when the universe was young. These clusters orbit our galaxy in random patterns, unlike younger star clusters that follow organized paths in the galactic disk. Omega Centauri, the largest known globular cluster in our galaxy, may be the remnant core of a small galaxy consumed by the Milky Way billions of years ago. Let's venture into the most extreme environments in globular clusters, their impossibly dense cores, where the laws of physics are pushed to their absolute limits. In the heart of a globular cluster, stars are packed so tightly that the average distance between them is just a fraction of a light year, closer than the distance between our Sun and Alpha Centauri. To put this density in perspective, while our solar system has vast empty spaces between planets, a cluster core fits hundreds of stars within the same volume. This extreme density creates a cosmic dance of chaos. Stars weave between each other in complex orbital patterns, constantly tugging and pulling on their neighbors through gravity. The density increases dramatically toward the core. The center can be millions of times denser than our local stellar neighborhood, creating conditions found nowhere else in the galaxy. These tight quarters lead to frequent stellar encounters. Stars can exchange material, merge, or even eject each other in a cosmic game of gravitational billiards. The chance of stellar collisions increases exponentially with density. In the densest cores, stars may experience multiple close encounters during their lifetimes. These dense environments are also perfect laboratories for gravitational wave astronomy, as massive objects spiral closer together in the crowded core. The constant gravitational interactions heat the core, creating a phenomenon called core collapse, where the center becomes even denser over time. Binary star systems play a crucial role in preventing total core collapse, acting like thermostats that regulate the cluster's central temperature and density. In the dense cores of globular clusters, we find something that shouldn't exist: stars that appear mysteriously younger than their neighbors. These are blue stragglers. Blue stragglers stand out dramatically from their aging neighbors. While most cluster stars have reddened with age, these rebels shine with a hot blue intensity. On the Hertzsprung-Russell diagram, blue stragglers appear where no stars should be, above the main sequence turnoff point. They seem to break the rules of stellar evolution. The secret lies in stellar vampirism. In tight binary systems, one star can steal material from its companion, gaining mass and appearing rejuvenated. If you are enjoying this cosmic journey through globular clusters, consider subscribing to join us for more space science adventures. Besides vampirism, blue stragglers can form when stars collide and merge. The dense cores of globular clusters make these cosmic crashes more likely. When stars merge, the resulting object has more fuel to burn, effectively resetting its evolutionary clock. It's like getting a fresh start in stellar life. The denser the cluster core, the more blue stragglers we find. This supports both formation theories. More crowding means more collisions and close binary interactions. These stellar fountain of youth processes are ongoing. Right now, in countless globular clusters, stars are dancing, merging, and stealing their way to renewed youth. By studying blue stragglers, we learn about stellar evolution, binary star physics, and the dynamic environment within globular clusters. Let's explore how globular clusters have endured billions of years of cosmic violence while maintaining their pristine nature as ancient time capsules of our galaxy's history. Their survival largely depends on their orbital paths. Most globular clusters inhabit the galactic halo, far from the destructive forces of the spiral arms. Through multiple galaxy mergers, these stellar cities have remained remarkably intact. Their intense gravitational binding keeps them together even as galaxies collide. The secret to their longevity lies in their incredible density. Stars are bound so tightly that even powerful gravitational forces cannot tear them apart. While open clusters dissipate over time, globular clusters resist tidal forces through their compact structure and strong gravitational cohesion. They continuously clean themselves, ejecting debris and gas from dying stars, which helps maintain their pristine nature and prevents new star formation. Despite losing some stars over time, most globular clusters retain 90% of their original mass, preserving their ancient stellar populations. Their complex internal dynamics help distribute energy evenly, preventing collapse while maintaining their spherical shape over billions of years. Those that survive today represent the most robust examples, having already weathered the most challenging periods of galactic evolution. These remarkable structures are expected to persist for many more billions of years, continuing to serve as pristine laboratories for studying the early universe. As we conclude our journey through globular clusters, let us explore how these ancient stellar cities serve as crucial tools for understanding the deepest mysteries of our universe. Globular clusters trace the invisible dark matter halo of our galaxy, helping astronomers map its distribution and mass with unprecedented precision. By studying the oldest stars in globular clusters, scientists can determine minimum age limits for our universe, currently estimated at 13.8 billion years. These stellar fossils reveal how galaxies like our Milky Way formed, preserving chemical signatures from the earliest epochs of cosmic history. The metal content of globular clusters creates a timeline of galactic chemical evolution, showing how successive generations of stars enriched our galaxy. Globular clusters will likely survive the future collision between our galaxy and Andromeda, continuing to orbit the merged galaxy as eternal witnesses. These clusters help reconstruct our galactic history, revealing past mergers and acquisition events that built our Milky Way into what we see today. Their incredible density makes them perfect laboratories for testing gravity, potentially helping us understand modifications to general relativity. From dark matter to galaxy evolution, globular clusters continue to provide crucial insights into the fundamental nature of our universe. As we end our exploration, remember these ancient clusters continue their eternal dance, preserving secrets of our cosmic past for future generations to discover.